let me continue where I left off last time. We had this big sphere, and we verified that for every area here on the sphere, the light, or the lines coming out of it were distributed in such a way that their expectation was constant per unit area on the sphere per unit, per unit area perpendicular to the line direction. So this area perpendicular to the line direction per solid angle. Which means, the way I define this line radiance as the expected number of lines. It's like the expected number of photons coming off in a given direction to determine radiance. And now what I want to do is I want to consider any other piece of surface here, say DC, which is actually a little piece of an object in the scene. It could be a smooth surface or a polygonal surface. And I want to show that the number of lines that hit it is proportional to its area. That was one of the claims in the book they made for these uniform lines. And so what I'm going to use is, here, let me just make it, forget the surfaces that was on. If you think about these rays coming to fill up this surface, that's going to define a certain solid angle. And the point is the expected number of lines measured by taking a point on here and finding the solid angle to this surface is going to be the same as if we take a point on here and find the radiance coming in from here. So if here's a point X and here's a point Y, the claim is that the line radiance measured from X in the direction from X to Y is the same as the line radiance at Y measured in the direction from Y to X. And the reason is that both of these can be explained in terms of the total number of lines that go anywhere between these two surfaces. And so the expected total number of lines between a surface on here and a surface here, that's what I call d phi squared. I think it was capital Phi squared. And this radiance equals, well, let me rewrite it so that I don't violate the principle of staying on one board. That's d phi squared. Okay, so we're measuring that per unit area. So that's dA perpendicular to the beam. So we need a cosine of this vector xy and the normal at, I guess, x. Okay, that's normal to the beam, and then we have d solid angle omega, and that solid angle omega is the solid angle that the surface DC fills coming to the point X. So for that, I can use my solid angle measure. So here I have my dA. Why don't I just say cosine theta x for short? And then this d omega is actually dC cosine theta y. That's divided by rxy squared, because that's the formula we use for computing solid angles of a surface that tilted to the beam. Right, so I've got my picture sort of filled up now. Let me take away the lines and draw. Here's the ray, for the direction from x to y. This is theta x. And if this is the normal, this is nx, this is ny, this one is theta y. Okay, but all I have to do is move the rxy on the other side and put it under the dA cosine theta x, right? Because they're all being multiplied together. If you put these over a common denominator and then take this away from the common denominator, right, then it looks like d squared phi times this dc cosine theta y times the solid angle at y subtended by the area dA, right? Because that's what this factor is. So this is exactly the same proof in the book that we skipped, but it's in the book, and I told you to read for conservation of radiance rather than line radiance, because this now is the radiance at y going in the direction yx. So either leaving here or coming in received here, it's the same radiance. That's conservation of radiance over through a vacuum with nothing obstructing it. Okay, so now I want to go farther. I want to actually figure out what that is. And we know that this one was something I computed last time. It was n over 4 pi squared r squared. I think that's what I got. Does that look right, what I got at the end of last period? Because it's not on my notes here. And that means this one also is going to be n over 4 pi squared r squared. And so now I want to look at the total lines hitting a surface SI with area AI. So that means what I'm going to do, this is equal to, I guess it's the integral of the incoming line radiance over the hemisphere at y over the area of y, sy, and that's going to be this constant L now, which is this number, because it's the same measured coming off the surface or into any other surface. And remember, we don't care about obstructions in there because the lines are continuing anyway. Of this constant L times d omega at y times cosine theta y, and then that integral times dA at y. So the outer integral is just going to be AI, and the inner integral is what? What happens when you, I'll take the constant L outside too, and what happens when you integrate cosine over a hemisphere? Say it louder. Pi. Okay, so you know that's proportional to the area, and the proportionality constant, if I multiply this L by pi, I'm going to cancel one of the pi squareds in the denominator, and I'm going to get AI times the factor n over 4 pi r squared. So the number of lines hitting any surface is proportional to that surface. That was one of the claims, that the first one I wanted to prove. And now I want to prove something about the form factor, that the form factor between two surfaces is proportional to the number of lines that hit them both. So I guess what I want to do then is look, maybe I'll draw another sphere here. Here's a sphere, and here's one surface, say AI, and here's another surface, AJ. And now my flux is going to be all the lines hitting surface AI, going through surface AI, and then through surface AJ. And so that flux, let's see if I can find the right page here. That's on a different page, page 6 of this one. Oops, there's 6. So this flux of lines, this is the expected number of lines between, say, if we say d squared between dax and day, we can look at that first line there and say that's equal to this number L times dA, which one is that? Did I write it? Yeah, this is the dax, say. And then times the solid angle, well, times cosine theta x, times now this is going to be the solid angle day is going to be cosine theta y day over rxy squared. So now our x, say, is here, and our y is here. They're both inside, but otherwise, this argument is the same about the solid angles. And so if we're going to integrate this over the areas, we're going to get the actual flux is the integral, say, over SI times the integral over Sj of this line flux. Let's put the cosine theta x, cosine theta y, dax, day over rxy squared. But there's one thing that I left out, that I should erase the dax, day for, and that is now we are considering visibility, right? Because if we have another thing interrupting these lines, we'll get lines from here to here, but the line that would have gone on through won't count as going between here and here. So then we actually have the visibility here. Visibility xy, dax, day. So I want this to end up looking like the form factors. And the only thing that's missing from the form factors is a constant pi here in the denominator. Right? So I'm going to put that pi in the numerator just so I can cancel it out. Okay, so what I can write is, what I've got here is pi L times an integer, which times a number, which is the form factor from patch I to patch J, multiplied by the area of I. Because I was supposed to have 1 over the area of I in the form factor. Okay, so suppose that is Nij, the number of lines. The expected number is going to be this, and a particular estimate of it is what we actually count. And so if I put in my L now, where was my L? N over 4 pi squared r squared. So I'm going to get N over 4 pi r squared for my pi L, AIFIJ. Okay, so the claim in the book is Fij is approximated then by the actual count Nij over Ni. Right, so if I have, is that true? The expected value of this one is here, and the expected value of the denominator is there. So if I take the ratio, it's N times AIFIJ over 4 pi r squared. And then by dividing by this fraction, if I put the AI in the numerator, it'll make it easier for me to do that. Let me just do that. I'll have 4 pi r squared times AIN. So the AI's cancel, the N's cancel, the 4 pi squareds cancel, and I get Fij. Right, so that completes the proof that they didn't give in the book, that this ratio of these two counts from those global lines will give you an estimate of the form factor. And the point is it gets all the form factors at once. That's the point. Okay, but now the scheduled topic, I guess it was even for last time, was the hemicube algorithm, which is another way of estimating form factors, but it's really going to estimate a differential form factor. It's basically a form factor, we say DAI AJ, where DAI is supposed to be a differential area. And so I guess the estimate you need is to, it's sort of a per area form factor for a small unit area. So what we're going to do is we're going to say, here is a surface. It could be curved, and here's a little piece of it, DAI, of units, small unit area. And we're going to just look at a single point on that. And what we want is, what is the form factor from all the other surfaces in the scene? Maybe I should draw polygonal surfaces here. In terms of how they're visible to this single point, say X, on this surface. And so we're going to compute the integral, let's see. So what this means, maybe I didn't prepare it in my notes, but what we're going to actually try and compute is the integral over all SJs of this product of cosine theta x cosine theta y over pi r squared DAY. And we're not integrating over the area but at x, but neither are we dividing by it. So basically, instead of getting an average of this quantity over the whole patch, we're just going to compute it at one point on the patch and assume if the patch isn't small enough, it doesn't vary too much, which is sort of a hack. But it's a way to estimate the form factors using graphics hardware. So what we do is you can think of a unit hemisphere here around X. Let me take away this little DAI because there's really no area. You're just doing it at the point. And so here's a single hemisphere at this point. I guess it looks too tall. Here, that looks more like half of a sphere. And what we're going to do is we're going to put half of a cube around it. This is supposed to be, parallel to the coordinate axes here. That doesn't look like it's tangent to the top because this part is already above the top. It's basically half as tall as it is wide. So it should look like something like this, I guess, in order to be tangent to the top of the sphere right here. And what we're going to do is we're going to use graphics hardware to project all these polygons onto the faces of the cube. So say you were projecting to the top face of the cube. Right? This thing may partly go down the side, but the way I've drawn it, maybe it doesn't. It probably, this one projects, let's see, this, if I go out this, because I guess my point X is in the middle here. I don't know. Let's pretend it projected completely on the top face here somewhere. What we have to do is say that what we can do in terms of the solid angle is measure this solid angle of its projection on the cube face. And that solid angle, both of these really represent area of some curved piece on the unit sphere. And so it doesn't matter if we compute that solid angle by integrating over this surface or integrating over the visible part in the hemicube. So what we'll do is we use computer graphics hardware to project this polygon onto this surface. And we'll project all the other polygons of the scene onto the surface too. So if we have a polygon here which is closer, the Z-buffer algorithm is going to overwrite whatever part of that polygon hid this polygon as a different polygon into the Z-buffer. Something like that. However, they overlap. And so what's in the Z-buffer is the color of the closest polygon. But we don't want the color, we want to know what polygon it was. So we project the scene we're actually going to render the scene, right, as projected on the 5 faces of the hemicube. Hemicube because it's a half of a cube. Hemicube with a polygon ID. That's an integer from 1 to the number of polygons instead of a color. So back in the old hardware days when you only had like 1 byte for red, 1 byte for green, and 1 byte for blue, that's still, 3 bytes or 4 if you have RGBA in the frame buffer, which is plenty to get, if it's 4 bytes, 4 billion possible polygons or something. So you've got a lot of potential IDs, and you can figure out what part of the hemicube was covered by that polygon. And now what we can do is we can figure out the solid angle of the polygon by adding up the solid angle of all the pixels that the polygon contributed to. So I'm not drawing these pixels very well, but there's a certain number of pixels whose centers are inside the polygon. I guess I'm just not drawing it in the perspective. Well, yeah, these are sort of like in the perspective of this face. So we get, as we scan convert the polygon, maybe we get these 3 centers on that line, but not these, and so on. So basically, if we can find the solid angle of each of these pixels, we can just add up those solid angles, and we'll get the solid angle of the projection of this polygon on the hemicube face, and that's the same as the solid angle that it uses to contribute to that integral. And so what this integral is going to be is, this is Rxy. So we have to have 1 over pi times the sum over all pixels p, so that Sj is visible in P, visible, what do I say, at P, right? That's basically 0 or 1. It's 1 if it's visible and 0 otherwise, times a delta form factor at P, where delta F at P is the solid angle of pixel P on the face of the hemicube. So there are different formulas for this solid angle depending on which face you're talking about. Suppose we make Z be vertical, X be this way, and Y be that way. So, I don't know, what do I call it? We'll call this pixel P then, so it doesn't look like the X here. P was the pixel name, so why don't I call the point, I don't know, S or something. I've got the center here, and I have, that's at the origin of this XYZ coordinate system, and now I have a pixel P whose coordinates, if they're on the top face, are x, y, 1. Right? And now, basically the pixel is a little square around that center of width dx in this direction and width dy in that direction. So its area is this dx times dy. It's a constant. It's basically the area of the top face, which goes from -1 to 1 in each direction, divided by the resolution. So this is 2 over x res, and this is 2 over y res. And they're both the same usually, because you want to divide it into a square grid. Okay, so now let's figure out what that's going to be. So now I sort of have to get this geometry. So here's my hemicube, and here's a point x, y, 0, and here's a point above it at x, y, 1, and basically at the origin here, oh, that doesn't look parallel. I'm trying to find the solid angle of this little square. So basically I have this angle theta. But actually theta is between here and the normal at x, at the origin, and here is the normal at the pixel, and it's pointing in the opposite direction, and this theta is the same. So what is cosine of theta? That's the length, let's see, divided by 1, right? Because this length is 1. Right? This is the height of this above the plane is height 1 in this hemicube. So cosine theta, it's an acute angle, so we only have to worry about these two lengths. What's the length of this? If we're going to pixel from 0, 0, 0, which is where my center S was, up to 1 xy, xy1, it's this. So basically I said it was r over 1, because this side was 1 and this side is r, and that's r is the square root of the difference in x's plus the difference in y's plus 1. So that's my cosine theta. So this solid angle is going to be dA cosine theta divided by r squared times cosine theta x cosine theta y. I guess I have a pi there. Well, yeah, let me put the pi in the delta form factor so I don't take it out. That's probably more convenient, because then I'm just adding them up. I don't have to multiply. Because basically I'm going to pre-compute these delta form factors for each of these pixels on the hemicube, and then I'm just going to add them up. So that means this is my dx dy, which I have in advance, and then the cosine theta, it's the other way around, not r over 1, it's 1 over r, the side adjacent over the hypotenuse. So that's 1 over that. Okay, so I have 1 over the square root of x squared plus y squared plus 1 for the first cosine, and then another 1 for the second cosine, and then 2 more for here. So it's actually to the 4th power. And that's dx, dy are constants. I just had them on the other board. I'm not going to copy that formula for them. Over pi, it's 1 plus x squared plus y squared. If you take the square root and then take it to the 4th power, that's squared. So that's the delta form factor for little pixel on the top of the cube. And now I have to draw a similar picture for the side of the cube. So let me draw the same cube here. Actually, this doesn't come that high, does it? It's more like that. That isn't a beautiful picture, but here was the top of it. And here's the side. And now if this is x, let's look at something on the face that's perpendicular to the x-axis. So a point here, if this is y, and I'm sorry, that's z, and this is y, we can think of a point here, a pixel whose coordinates are 1 for x, and then y and z. And now we have, actually it doesn't look right, this ray here, and we have a theta at the point S here, and another theta at the point P. And that looks to me like they're different. I can see theta P, because if you project this point to this plane here, this R is the square root of 1 plus y squared plus z squared. And cosine theta at P I should be able to find because, let's see, this is the side adjacent to it, and this point is 0, y, z. So this adjacent side is 1. So that is still cosine 1 over r, 1 over the square root of x squared plus 1 plus y squared plus z squared. But now what about theta s? Basically, what I can do for theta s is I'm basically projecting this point, I guess, perpendicular to the z-axis. And so here's a point which is 0 for x, and y is the same as it was, but no, let's see, what's the same as it? Y is 0, z is the same as it was. Sorry, is this the projection of this vector on the z-axis? Because the z-axis is 0, 0, 1, and you dot that with this and you get the z component, and then you multiply it by the vector 0, 0, 1. So that means that this dot product is the length of this divided by r. Right? So cosine theta at the point S is z over the square root of 1 plus y squared plus z squared. And that means that if I do the same thing, I'm going to get, now my pixel has a side dz and a side dy, and that area, so the delta form factor for this pixel is dy dz, and now I have the product of the two cosines. I have a z and a 1, so I'm going to get a z here, and now I'm going to have pi times 1 plus y squared plus z squared squared. 2 of the square roots from here, and 2 for the 1 over r squared. So I can get, similarly, for this face, I'm going to have the same formula, and for this in front and back faces of the hemicube, this face here and the back one, it's going to look like x and z with y equal to going away from it. So it's still it's basically the same formula, except I'm going to get x squared plus z squared instead of y squared equals z squared. In fact, I don't even have to pre-compute all of these, because basically the pattern on this half of this side is the same as the pattern on that half of that side. Right? Because it's y squared, it doesn't matter whether it's plus or minus. And in fact, each of these halves of the hemicube are repeated on each of the vertical faces. And on the top face, each quarter is repeated. Right? Just reflected on x or on y. In fact, for the top face, you only need a triangle's worth. Right? Because this other triangle can be reflected around this 45-degree line. So back in the days when it was really hard to save memory, even of one frame buffer's worth, you could actually not save them all, get them by symmetry. But nowadays, it's probably easier to just have simpler code that doesn't have the symmetry and just fetch them all. So the loop basically for the I don't know if I even have it here. I've got so many pages here. See if I've got my loop. I don't, but I'll make it up. So for all j, first we have fixed I, fixed patch I. Maybe we're going to compute it over for all I later. But for the one hemicube based at I, we're going to set Fij equal to 0, and then compute and read back ID buffers for hemicube faces, and for all pixels P, we're going to look at the F. We're going to say J equals the ID buffer at pixel P, and we're going to increment Fij by the delta form factor at that pixel. And when we're done with this loop, we'll have the form factors of each face from this patch I. And if we assume it's the same over the whole patch as it is at just that single point, we've got an estimate of the form factors. Okay, now I want to try, at least to start, to give a new twist on this algorithm, which I actually suggested, I don't know, 20 years ago, which is another way of representing the radiosity. Because imagine you have a scene built out of a lot of triangles. What I suggested was, if you have a vertex here, you're going to get the radiosity at each of these patches, and then you're going to average it at the vertex for the purpose of shading the vertex. And then, if you do the average over each of these vertices, you can linearly interpolate across the triangle using Gouraud shading. And that linear interpolation is actually going to give you a better approximation of the radiosity, because the radiosity is really varying smoothly. So certainly a piecewise linear function can better represent it than one with jumps, as you have with a constant shading per facet. Okay, now, so let's assume now an approximation of the radiosity at the point x as the linear interpolation to the x of the radiosities at the vertices. So how are you going to do that? One way to do that is as basis functions. Like when you have piecewise linear interpolation of a bunch of function values, you have a value here, and a value there, and you want this straight line. What you can do is represent it as the sum of a bunch of hat functions. This weight times this hat function plus that weight times that hat function if you look on this segment here, this plus this adds up to this straight line. Right? And the only hat functions that contribute are the two at the endpoints of the interval. So in this case, the only we'll have tent functions then. They'll like be pyramids. There'll be 1 at a vertex and 0 at the others. This is weighted hat function weighted by the height here. So our weights are going to be the bj at the vertices, and this is going to be the sum over the vertices of piecewise linear function nj of x, where nj on, if this is bj, nj of x is the function which is 1 at this vertex and 2 at these other vertices. And if I have an x in a triangle that doesn't share that vertex, then it's going to be 0. Right? So, you know, on a vertex, if I do a side view of this vertex, it's like a triangular pyramid. In this case, it's a pentagonal pyramid, right? Okay, so with that representation, then, we can write a radiosity consistency equation that says that the... See, I think I have it better on another page here, where say B at vertex I is the emissivity, assume we have emissivities defined per vertex, and now plus the integral, say rho I, times the integral over all surface areas, sum of j, of this radiosity formula, b of y times this k x y, which had our this was this factor plus the times the visibility, times day. So this is ei plus rho I. This is the integral over all. It was integral over all surfaces, but if we put the sum outside here, we can have the integral over just Sj of k x y, and then we only have 3 vertices times, I didn't really leave room for this factor, so it's a b, j1. J1, j2, j3 are the 3 vertices of the triangle containing y, n1 at y, nj1, say, plus b, j2, nj2 of y, plus b, j3, nj3 of y. Times k x y day. So if we represent this as a form factor, we can have vertex-to-vertex form factors. So it's the sum, let me write the EI, plus rho I, the sum over vertices j of f ij times the radiosity at that vertex, where fij is now going to be which of these terms contribute for that vertex. And let's see if I can look at my notes now. I've gotten ahead of my notes. And see what that vertex-to-vertex form factor is going to be. Fik is the sum L equals 1 to nk. That's k is the a vertex, and nk is the number of triangles that share that vertex. and we're going to integrate over each of these triangles, say JL, that's J stands for the subscript for the L's triangle, of NKY cosine theta x. Sorry, wrote this wrong. I'm writing the geometric factor now. Theta x cosine theta y over pi r squared. I guess I'm going to have times the visibility of x, y, d, a, y, where ay is integrated over each of the triangles sharing vertex k. Right? Because this is my kernel, and this is getting, for each vertex, it's picking up part of this term. Here this is a sum over triangles, but now it's a sum over vertices. But I'm still picking out exactly, for each triangle, I'm getting the part of that triangle that is one of these three things that actually has that vertex there in the sum. So I can do this by a hemicube calculation also. Basically, this thing is pi times this, and this is pi times the solid angle. The visibility comes out from my buffer, but I need these functions. So for any triangle, for this vertex, we'll do it later. Say I have a u barycentric coordinate and a v barycentric coordinate, and then that means the weight for this vertex is that barycentric coordinate, because that's the barycentric coordinate that's 1 here and 0 on the other two. And similarly, this one represents the function that's 1 here and 0 on the other two, and 1 minus u minus v represents the 1 here. So give me one more minute. This is actually beeping a minute before, but it might take me a minute after. What I have to do is, in my buffer, I'm going to store u and v, say, as the red and green buffer values. So store u and v as the colors in red and green, and then blue, and then B and alpha have the ID. Okay, so with modern frame buffers, you have enough for lots of polygons because they're each 32 bits. But before that, that was only 2 bytes worth is what we used. We didn't have that many polygons. And now when you read back the frame buffer, what you need to compute this sum is, it's going to be either a u or a v or a 1 minus u minus v to get the contribution of a pixel that represents some point inside the triangle to this kind of sum, depending on which vertex of the triangle was showing up here for this kth one. And so you can do a similar thing, so that you're going to say, for that pixel, instead of just incrementing 1, you're going to say f I j1, where that's one of the vertices of the triangle, equals u times delta f for the pixel, f I for the other vertex. You have to have a table saying, which vertex is which on each triangle. And f I, this should have been plus equals 1 minus u minus v, where you get them from the colors, times the same delta fp. And you're actually estimating the vertex-to-vertex form factors. And this method is called point collocation. The previous one, where you were integrating it, a double integral, that's called the Galerkin method for finite elements. And this method of vertex-to-vertex form factors is called the point collocation method, because you're actually making a consistency equation for the radiosity on vertices. You know, this is really only an approximation if you write it like this, right? Because the true radiosity isn't a linear function either. But this is a way to solve a similar system of linear equations for vertex radiosities instead of patch radiosities. And it's a better approximation because piecewise linear is a better approximation than piecewise constant. And you can also do it then using the hemicube. And that was the point. This was published in the first graphics gems book that came out about 20 years ago. Okay, that's it. Sorry I ran late.